Hi, we are Team Taco Tuesday, and our project is on the quesadilla hot plate temperature optimization. Our group is composed of Estanislao Bravo, Jackson Lowe, and myself, Michael Ellsworth. So just a brief overview of what we're going to talk about today. We're going to go over an introduction of our project and what we worked on, our apparatus and our simulation model that we used to work on our project, and then just a brief overview of the theory behind how the project works, talk about our results in our discussion, and then lead on to some conclusions from that. So our project is on quesadilla hot plate temperature optimization. And we found that, in our lives that sometimes it's hard to be able to keep your hot plate at the correct temperature to keep the quesadilla cooking without burning it. And so our objective was to determine which heating parameters were necessary to maintain the hot plate at our optimal temperature for cooking quesadillas. So in our prior work, we determined that to be 75 degrees Celsius, and with that 75 degrees Celsius, there's about a 2 degree window where we're okay with that air.
All right, so we, even though most of our programming for our hot plate was based on a physics-based model, we used our Arduino to simulate data and see how our heater would respond to our temperature control parameters. One difficulty, though, in creating our 4-celled hot plate by using an Arduino is that our hot plate's heat transfer from cell to cell are mostly based on conduction, whereas the Arduino, the heat transfer of the Arduino is mostly through radiation and convection. And so the Arduino gave us a rough idea of how we could simulate our hot plate. And the way we modeled our hot plate was basically with 4 cells, all having their own heater, and it was based on 3 different types of heat transfer: conduction, convection, and radiation. We set up energy balances on those 3 types of heat transfer between adjacent cells. And in our code, we used the properties of a typical aluminum hot plate, like the thermal conductivity and emissivity and mass. And using these properties allowed us to scale up our heat response to the appropriate size of a typical hot plate. And ideally in the future, more than 4 cells will be used to accurately model the heat transfer of the hot plate. And Bravo will talk about some advantages of that later. But here are some equations that we used while doing this physics-based model of our hot plate. We have this PID controller method that we used, and we gathered our tuning correlations from graphs that we simulated using our physics-based model, and then our temperature simulation. This nasty long equation here is the change of temperature for the first cell. So the first cell is adjacent to the second to the right and the third to the bottom. So all these terms, we can go over them briefly. The first one is the amount of heat that's lost through convection to the ambient air. The second one is the amount of heat that's lost through radiation or emissivity to the air. This third term is convection from the second plate to the first plate, radiation from the second cell to the first cell, and then we have conduction and convection and radiation from the first and third cell as well. And so we modeled that between each of the 4 cells to give us proper readings on their temperatures.
And using the simulation that was just explained, we were able to get a temperature response from the Arduino to find our initial parameter values. We used those initial parameter values in conjunction with our tuning parameters to optimize the values that we got. and we were able to get the following values that are shown here in this section. We did find that using the values that are some square errors was larger than we anticipated at a value of about 18,000. But given the large data set that we gathered, we concluded that this value is acceptable within the simulation, and we were very pleased with the results that we were able to get. Also, in the future, we plan to improve our model by using thermocouples to gather data directly from an actual hot plate. We believe that this will be able to help us evaluate how conduction, convection, and radiation affect the neighboring cells in a more accurate way. We also plan on conducting research on larger matrices of hot plates. At the moment, we only have a 2x2 array for our hot plate. We believe that with more time and more resources, we can build higher models. In conclusion, we were able to find accurate control parameters from our simulations that fit the model that we built, and we have plans to improve our model in the future and testing higher order systems. We thank you for your time.
Thanks. Go Tacos.
Go Tacos.